Then we move on to visualization. So we begin by importing matplotlib plt as plt, importing seaborn as sns. So we did plt figure fig size equal to 8 to 5. Basically, this creates a new figure with like dimensions of 8 inches width and 5 inches height. And then we move on to axis is equal to sns to count plot x heart disease and data df. Basically, this uses seaborn's like count plot function to like create like a bar chart showing like the count of observation for each of the category in like the heart disease column. So 0 for absent and 1 for present. Next, we move on to ax.bar label ax containers bracket 0. Basically, this adds like a numerical label on top of each of the bar, showing like the exact like count of each. Then we retitled the plot, then we label the x variable, the y label, and then we basically plot it. Next, we calculated the percentage of each by using heart disease percentage equal df heart brackets heart disease that value counts normalized true times 100. Basically, this calculates like the percentage on each category in the heart disease column. Next, we move on to print percentage of patients with heart disease percentage, brackets 1 with 0.2f, then percentage of patients without heart disease with heart disease percentage, bracket 0.2f. Basically, this prints out the percentage of patients who have heart disease and who don't. So as we can see from the visualization here, the people who don't have heart disease are like 410 as opposed to people who do have heart disease, which is like 508. And the percentage of patients with heart disease is like 55.34%, and the percentage of patients without heart disease is 44.66. Basically, this showing that this distribution is slightly imbalanced as there's more people with heart disease as opposed to no heart disease. Next, we move on to continuous features is equal to age, resting BP all the way up to old peak. Basically, this line of code basically identifies like continuous variables that will be like visualized. And this section is important because these are specific features that are clinically relevant to like the heart disease prediction. Then we do fig axis is equal to plt.subplot all the way to axis is equal to axis.flatten. Basically, this creates like a figure with a 3x2 grid of like total space of 6 with like for the 5 features over here. Next, we move on to 4i features in the enumerant continuous features all the way to axis brackets I ledge heart disease and no heart disease and heart disease. Basically, what this block of code does is basically this loops creates like a histogram with like the kernel density is equal to true for each of the continuous feature segment. Then the segments the data by targeting the target variable heart disease using like the heap parameter. Then it adds the appropriate titles and labels to each of the subplot. Basically, it shows us how each of the continuous various distribution different from like patients with and without heart disease. And then we move on to if length continuous features is less than length axis, fig the axis axis brackets 5. Basically, this line of code is to show if we have like an empty subplot, since we have like 6 subplot spaces but only 5 features, it removes like the last one, and then we plot and like show it. So here's our graph. Here's a distribution of age by heart disease, as people who have heart disease usually are peaked around like from 40 to like 60, as opposed to people who don't have heart disease, which is around like 45 to like around like 65. Then the distribution of a resting BP heartbeat. Then we have like distribution of a cholesterol by heart disease visualization over here. Then you have the distribution of max HR by heart disease, showing like that people who have heart disease basically start increasing at like around 120, as opposed to people who don't, who have like 80. And then we move on to this distribution of old peak by heart disease between like no heart disease and heart disease people. So yeah. Next, we move on to creating a correlation matrix. So plt.figure fig size is equal to 12 to 10. Basically, this creates a dimension of 12 inches by width and 10 inches tall. Numerical df is equal to df.select type. The types include brackets np.number. Basically, this creates like a new data frame that contains like only the numerical columns from like from the original data frame dataset, as like correlation analysis can be performed only on using like numerical data. Then we move on to correlation matrix is equal to numerical df.correlation. Basically, this calculates the Poisson correlation coefficient between each pair of like the numerical columns in the dataset. And then we move on to SSN heat map with these parameters all the way to the plt.plot. Basically, this creates the color-coded heat map for the correlation coefficient between like each of the numerical columns. So here we have the correlation matrix of the numerical features. So as we can see, the redder it is has a higher correlation as opposed to bluer it is. For example, something such as like Old Peak has like a higher correlation with heart disease as opposed to something like Max HR, which has a lower correlation with heart disease. So yeah, next we move on to the print correlation with the target variable in descending order. Basically, target correlation is equal to correlation heart brackets heart disease, sort value is ascending is false. Basically, it's printing out all the correlations in a descending order. So here we have the correlation with heart disease. So right now we have heart disease at 1, and then so it's all the way going down to like max HR, which has a negative correlation with heart disease.